Welcome back to week 2 of the ma135 ma160 calculus. My name is Götz Pfeiffer and this video is about the definite integral. We've seen how an area under the curve of a function, under the graph of a function, can be described as a limit of a sum of areas of approximating rectangles. On the basis of that, we now define the definite integral as follows. So we have a function f of x, which is defined over the interval from a to b, defined for all values of x between a and b. For any natural number n, we can subdivide this interval from a to b into n smaller intervals of equal width, which then would be b minus a over n. Denote this by delta x. And then this results into new points on the x-axis, new points in addition to a, which we call x0, and b called xn. And there's x1, x2 up to xn equally spaced out between a and b. Then in a slightly more general procedure than what we looked at earlier, for each sub-interval, for each I between 1 and n, there's a sub-interval ranging from xi minus 1 to xi, and in this sub-interval we pick a sample point and call it xi star, and then we define the definite integral of the function f from a to b through this notation, which we pronounce as integral from a to b of f of x dx. Define this as before as the limit as n goes to infinity of this sum of areas of approximating rectangles, if you want, or just as the sum of these products f evaluated at xi star times delta x. Where of course the delta x here, b minus a divided by n, changes with n going to infinity. This delta x, for each n, delta x is a different one. And the definite integral of f from a to b uses this notation. Integral from a to b f of x dx is defined as a limit of this sum of n terms of products of delta x with f evaluated at xi star, where xi star is some sample point in this ith subinterval from xi minus 1 to xi. So this is a limit. Limits might or might not exist. So this definition only makes sense when the limit exists and when it is uniquely defined, that is independent of the choice of the sample points in the interval. If the limit does exist, we say that the function f is integrable on the interval from a to b. I want to emphasize this again. The definite integral, with this notation, integral from a to b f of x dx, by definition is a limit. Limits may or may not exist, as we've seen in the semester 1 calculus. So this integral only exists when this limit exists. This integral may not exist. We are mostly interested in cases where it does exist. We're mostly interested in cases where the function in question is a continuous function, Now one can show that if f is continuous on the interval from a to b, then the integral exists, then f is in fact integrable from a to b. And in this context of continuous functions, we can always choose as our sample points the right end points xi of the interval, of the smaller intervals, of the right xi is the right end point of the ith subinterval, and then the defining formula for the integral simplifies to the limit as n goes to n of the sum for I from 1 to n of f of xi times delta x, and where the delta x is the entire width of the interval b minus a divided by n, and the ith endpoint xi is the left end of the interval a plus I times the length of a subinterval. Now that's the formula we'll be working with. So as an example, let's try and go the other way. Let's try and express this limit as n goes to infinity of a sum of n terms, and where each term is xi cubed plus xi times sine xi delta x. Let's try and express this as an integral on the interval from 0 to pi. So this is basically a pattern matching exercise. If we compare the formula here in the sum with the formula in the integral, we see that it makes sense to choose as the function in question, choose as f of x, the function defined as x cubed plus x times sine x. The endpoints of the interval here are given as 0 and pi, so we choose 0 for a and pi for b. And then on the basis of the definition of the definite integral, this limit as n goes to infinity of the sum of n terms of the form xi cubed plus xi sine xi times delta x is in fact the integral from 0 to pi of x cubed plus x times sine x dx. And note how in this process the sum symbol, this large sigma here, is replaced by the integral symbol, which is another version of s, like sum, that they chose at the time to represent the integral. It's a stretched version of an s there. Then the sample points xi used in the sum formulation become just x, just the continuous variable x here in the function description for the interval, and the delta x, which in the sum stands for the width of the subinterval, 1/n of the entire width of the interval. Delta x turns into this infinitesimal dx, which is part of the integral notation, which was also part of the notation used for derivatives in semester 1 calculus. We've motivated the definite integral with the area problem. I want to look briefly at a different problem which leads to the same kind of sums or limits of sums, and so it presents a different kind of problem which can equally well be solved, or to begin with described, by definite integrals. This is to be an illustration of the fact that the notion of integral is much wider applicable than just to area problems. But of course it's good to have the area problem as a motivation, as an illustration of the definite integral. So let's look at the distance problem. Let's try that distance problem. Let's look at the problem as follows. Let's try and find the distance traveled by an object during a certain time period when the velocity of the object is known at all times. Or let's say for starters, here we have a list of velocities measured at 5-second time intervals. And the concrete question would be, what distance does the object travel if the measured velocities are like this over a total time period of 30 seconds? And of course, at a constant velocity, the distance traveled is determined by the simple formula: distance is velocity times time. That's in a way reminiscent of the area formula for rectangles, isn't it? Anyway, here we're talking about distance, and the distance traveled at a constant velocity is that velocity times time. So, using this simple formula as an approximation for the distance traveled over this 30-second period, now we can take let's take the velocity at the end of each 5-second time period here as an approximation of the velocity over the previous 5 seconds. And then we obtain an approximation of the distance traveled as the velocity 9 here over the first 5 seconds, 9 times 5, plus velocity 10 over the next 5 seconds, that's 10 times 5, plus the velocity 12 over the next 5 seconds, plus velocity 13 over the next 5 seconds, plus velocity 12 over 5 seconds, plus velocity 11 over 5 seconds. This all multiplied out and added up gives a total of 335 meters. And if this looks familiar, this is because this approximation is of a form of, this is a sum of products of a form that we've seen before in a different context. It has the form f of t1 times delta t plus f of t2 times delta t plus f of tn and so on, f of tn times delta t, where the delta t is the 30 seconds split into n time periods of equal length, 5 seconds in the example we looked at. The intermediate time points ti are t0 plus I times the delta t. The first point t1 is 5 seconds, t2 is 2 times 5 seconds, and so on. And f of t is the velocity from the table here at time t. And this is a formula which gives an approximation of the distance traveled. And if under ideal circumstances the velocity, as it says here, is indeed known at each point in time, then one could determine the exact distance traveled as the limit of refined time periods, letting the n go to infinity, subdividing this 30-second time interval into smaller and smaller, more and more subintervals, and then evaluating this sum of products in the same way. The limit as n goes to infinity then would be an exact description of the distance d traveled. It's a different problem solved in the same way through a formula that serves for us as a definition of the definite integral. We'll see more applications of definite integrals beyond just area problems. Before we get there, let's look at a list of useful properties of this definite integral, properties which can be justified in a mathematically strict way. We don't want to do this now. We rely on the geometric justification of these properties. And they're as follows. The integral from a to b of a constant function, c, with respect to x, is just c times b minus a. That's the area of a rectangle, as we've seen. The integral from a to b of a sum of two functions, f of x plus g of x dx, is the sum of the integrals over f and over g individually. Number 3, the integral over the c multiple of f of x is the c multiple of the integral over f of x. The integral, number 4, integral of a difference of two functions, f of x minus g of x, is the difference of the integrals of f of x and g of x taken individually. Number 5 is a sum of a different kind. Here we talk about an intermediate value c in the interval from a to b, and following this idea of slicing up an area into vertical strips, and the integral from a to the intermediate point c of f of x dx plus the integral then onwards from c onwards to the end point b of f of x dx is the same as the integral all the way from a to b of f of x dx. Number 6, if f of x is greater or equal 0 for all choices of x over the interval from a to b, then the integral from a to b f of x dx will be greater or equal 0. More generally, number 7, if f of x is greater or equal g of x over this entire interval, then the integral over f of x will be bigger than the integral, greater or equal than the integral over g of x. And finally, if f of x is squeezed between numbers little m and capital M all the way between x, between a and b, then the sizes of the rectangles little m times b minus a and capital M times b minus a are lower and upper bounds for the actual size of for the actual value of the integral from a to b f of x dx. These properties can be justified one by one through the underlying geometry. If you want to take the time, go through them one by one, do a little sketch of the situation and see how the geometry justifies each formula individually. Property number 8 can be justified in a mathematical way by combining properties 7 and 1, if you want to try that. Here I want to apply these properties to quickly calculate integrals. The property of sums and multiples of functions. Integrals of sums and multiples of functions allow me to evaluate the integral from 0 to 2 of 4 plus 3x squared dx as follows. 4 plus 3x squared obviously is a sum, so the integral over the sum is the sum of the two integrals. The integral over 3x squared is 3x squared is the 3 multiple of x squared, so I can write this as 3 times the integral from 0 to 2 of x squared. And then property 1, or just, this is the constant function integral, constant function area from 0 to 2. This gives 4 times 2 minus 0, gives 8 as the value of this integral. And if you recall the previous video where we found the integral from 0 to 2 of x squared dx to be 8/3, we can now put them together to find the value of the integral in question is this 8 plus 3 times the 8/3, which is 16. Now here in this example we're given the value of the integral from 0 to 10 over some function f of x dx as 17. We're given that the integral from 0 to 8 over the same function f of x dx is 12. Question is, what is the integral from 8 to 10 f of x dx? Well, property 5 was about these intermediate points in the interval. It says the integral from 0 to 8 plus the integral from 8 to 10 equals the integral from 0 to 10, always for the same function f of x. So rewriting this, solving this equation for the integral from 8 to 10, we get that this integral is the integral from 0 to 10 minus the integral from 0 to 8, which is 12, which is 17 minus 12. And that's 5, of course. Now here, final example, we can use property 8 to estimate an integral. What is the integral from 1 to 4 of the square root of x dx? Well, square root, integrals of square roots, we'll do this properly later. For now, let's just note that the minimum of this function, the square root function, on the interval from 1 to 4 is the root of 1, which is 1, and the maximum, the absolute maximum of this function over the interval is the root of 4, which is 2. So as in the diagram down here, the graph of the function between 1 and 4 is sandwiched between the constant 1 and the constant 2. And so the value of this integral must lie between little m times b minus a, which here is 1 times 4 minus 1, that is 3, and the capital M times b minus a, which is 2 times 4 minus 1, which is 6. And this is using property 8 to give an estimate of the integral. Finally, I want to slightly switch the point of view and regard such a definite integral as something with a variable upper bound x. Let's regard this integral now in terms of a variable t, integral from a to x f of t dt. With a variable x, this defines a function that depends on x. This is defined, if we regard this as an area measurement, with variable upper bound x here, defines an area function a as a function of the variable x here, which is the upper bound of this integral. To make this more concrete, let's say the function in question is the function half of t plus 1. We can draw its graph, and in the concrete case where a is 1 and x is 3, we can calculate this integral from 1 to 3 over this function half of t plus 1, draw a sketch and determine its area. I won't go through the details, leave this to you for now. This is something we can do. There's a simple or two simple geometric formulas which give us the area from 1 to 3 of under this blue line. Then, after going through this procedure once, maybe twice for another choice of, maybe choose 4 as an upper bound next, and then 5. Eventually you will find how for any x bigger than 1, you can find a formula for the area of the region under this line from t equals 1 to t equals x. A formula in terms of x. An expression for the area as a function of x. This can be worked out with simple geometric means. Again, I'll leave this to you. And then finally, use the calculus 1, last semester's knowledge of derivatives, to find the derivative a prime of x, the derivative of the area function defined in this way. And do you notice anything? Is there a surprise? So that's the definite integral. We've defined the definite integral following a couple of ideas, namely that the area of a region divided into parts can be described as the sum of the areas of the parts. We've seen that we can approximate areas by areas of similar but simpler shapes. Finer subdivisions of a region give us better and better approximations. And using these ideas, we've defined the definite integral of a function f of x for x from a to b, denoted in this way, integral from a to b f of x dx, as a limit of increasingly better approximations of the area under the curve by rectangles. We've seen that the solution of the distance problem involves the same kind of sums as the solution of the area problem, indicating that definite integrals have a wide range of possible applications. We've seen a list of useful properties of the definite integral that help with its calculation or estimation, and we've seen one of the typical properties there are nice properties of the kind that the integral of a sum is the sum of the integral, and so on. That's it for now. Next week we look at the fundamental theorem of calculus, which drastically will simplify these calculations.